So putting more detail to this on how hybridization occurs to generate the 4 sp3 orbitals that are needed to make methane and other carbon centers with 4 single bonds at that carbon. We'll describe that here. So again, the quantum mechanical handling for this hybridization process is as shown. An s orbital is mathematically blended with 3 unique p orbitals. So this was the previous sort of energy level diagram for the orbitals, and we're going to get an outcome of sp3 orbitals coming out. So the process must be quantized in that if 4 atomic orbitals go in to the blending exercise, 4 hybrid atomic orbitals must come out of the exercise. Okay, so here 4 atomic orbitals, 3 p orbitals, 1 s orbital are going to come out. We need to generate 4 sp3 orbitals as the product. And the result here is shown. These new sp3 orbitals look like offset or asymmetric p orbitals. Notice that the positive phase of the 3-dimensional wave in these hybridized orbitals is larger than the negative phase. So that is the purple lobe is larger than the negative lobe. And this results by having the thought exercise of having this positive phase of this p orbital adding constructively to some of the s orbital to emphasize that atomic orbital into a larger lobe at that site. Conversely, the negative phase here is going to take away from any overlap on the other side. So this is of opposite phase is going to destructively add to the s orbital on this half of the atom, and we will end up with a smaller lobe at the left-hand side. So that explains how we end up with the smaller lobe here for this hybridized atomic orbital. Okay, the same can be said for the other 3. Notice that we've just arbitrarily positioned these orbitals all pointing the same way, but their characteristics of their orientation are going to be set according to the characteristic that was used in the exercise. So if we generated 1 sp3 orbital from s and px coming together, the orientation is largely going to be aligned with the x-axis of the Cartesian coordinate system. Okay, let's clean that up and make room for some of the next content. Okay. So when you now position those hybridized atomic orbitals over top of the nucleus, which would be here at the center point of those asymmetric dumbbell type hybridized orbitals, you can see that they now lie at 109.5 degrees from one another, which aligns with the bond angles that we typically see at a carbon with 4-fold single bonding. Okay, so shown here are only the purple lobes, the positive lobes, at that center point of the carbon atom. The negative lobes have not been shown for clarity, but you might expect that they stick out behind the lobe of interest. So in this hybridized sp3 orbital atop, there would be a negative lobe directly below it if that lies on the vertical axis of the Cartesian coordinate system. Okay, with that, you can see that these new hybrid orbitals were based on 3 parts p and 1 part s, and they now look asymmetric. They arrange themselves in a tetrahedral geometry, which aligns with what we see for carbon in many 4-fold single bonding situations. And these can be used to form 4 sigma bonds if we can bring in other nuclei. So if this was the carbon atom, as we said a moment ago, if a hydrogen atom comes in with its s orbital, we can now constructively add these 2 phases together and establish an orbital here that brings the carbon atom and the hydrogen atom together, and this would give us a sigma bond. Okay, so that's an example. These sigma bonds are free to rotate, so the carbon would be allowed to turn about that axis because of the sigma character to that bond. Okay, just clean that up. Okay, so sigma bonds, they have head-on overlap of an atomic orbital with a hybridized orbital, or they result from a hybridized orbital with a head-on overlap with another hybridized orbital. These give us very strong bonds. These sigma bonds are very strong. Electron density is symmetric about the axis joining the two. So that is, there's a symmetrical cylinder, quote unquote, of electron density, or the wave around the axis joining those two atoms together. And a single sigma bond is rotatable because of that. Okay, so we've seen here that hybrid orbitals can give us sigma bonds, and of course atomic orbitals can do the same as well. So in the case of hydrogen dot coming together with hydrogen dot to make the H2 molecule, we saw that two s orbitals coming together. You could also imagine a p orbital having positive constructive interference with an s orbital to give us a bond as well. So you would see that in forming CH, C, and NH and OH bonds. And the p orbital would be used from unhybridized centers at a carbon, for example. You can also form these sigma bonds from a p orbital with a p orbital. So in certain carbon, nitrogen, carbon, oxygen single bonds, p orbitals can form from CNO and will be hybridized.